Alrighty. Um, so I had to restart my computer again. Think there was another update or something, but I'm I think I'm good now for today. I think we'll be stable. I have no idea what's been going on. All of a sudden, after I had like one update come at me, I just start crashing every time I loaded up Visual Studio Code. But looks like I'm here now. Um, Before we actually continue on from yesterday, let's do some customization related things. So right now, whenever I start my terminal, right, I actually get a regular GNOME terminal, and I actually always have to type tmux manually to actually get into a tmux session, right? And I'm still trying to learn tmux and getting better at it. And I feel like if I don't start tmux right away, I'm gonna be prone to like falling back into the habit of not using tmux and then starting to like use tabs again, right? Instead of creating new tmux windows and splitting my panes and things like that. So I think in Stack Overflow there was like a question that says, how do I like always start tmux in every session? There was like a snippet of code, right, that um that showed how you can actually put this into your like bash rc, and if you actually uh start up any other terminal session, this piece of code in bash rc would always run to kind of check if you're in tmux, um or if not. And if you're not in tmux, then the tmux session would start automatically, so it would be like typing tmux for free. And if you're already in a tmux session, then it doesn't do anything, right? So I think it's we can just search for real quick. And I think I'll write write these in notes too. C24 08 was 11. So always start tmux. Uh-oh, typo. Tmux script. Okay, and then we'll have this be all ready for us. I think it's just bash. Okay, so it's like always start tmux in terminal, right? And then I think it's right here. How can I set my default shell to start up tmux, right? And I believe this one is the one, right? This is the copy paste thing, or there's also these types of suggestions that seems to work. I think the one I ultimately ended up using was this one here. I just arbitrarily um, never tried the rest, so I'm gonna just copy that here and I'll reference that question here, and you'll be able to use this piece of code later. Um, so let's put that into our bash rc, right? So if I do vim tilde bash rc, and I'll go to the last line of this file. The way to do that in Vim is just to do Shift G. You'll be taken to the last line, right? Then type O. You're all in command mode still, right? To insert a new line and go into insert mode automatically. And then just do Shift Control V. Oops. Actually, I need to copy this again because I had messed it up, right? Okay, so type O when you're in the command mode or normal mode, and then Shift Control V, and there you go. You have this in here. You're gonna go back into normal mode or command mode, where you call it :W :Q source dash RC, and now we're in tmux. Yay! So let's test that out. Let's close our terminal. Let's start our terminal again, and we're in tmux. This is great. Um, yeah, so I'm happy now. So this way I won't, you know, fall into old habits and starting a normal terminal and then having to go to like, start up new tabs when I can just do Control B C to get into a new window, right? So I like it. I think tmux is good because it allows me to multitask without having to juggle a bunch of terminal windows around. Okay, so yesterday, I think we left off where we had a little echo clone, right? Um, so I think the restriction that we had for ourselves was that we would only echo or at least print out the second argument given, which is like in this case, if we were to go back, oops, I think it's C, right? Come on, project C. Yeah, there we go. So average echo, all right? If we were to have like, let's say do something like a echo, right? Okay, so then like only the first argument, which is basically our second value, because our argv always contains not just the arguments after the program name, but also the program name itself, right? So we were only considering the second value and on or just the second value. And today I want to maybe try to extend this and actually consider not just the second value, but the rest of the values that follow afterwards. Because in real echo, we can do something like this, hello world, right? Let me just maximize that. And it'll actually, even though we have a space, right, after this, we actually still are able to output the entire input coming in, right? So it'd be like, our thing one, thing two, thing three. That would still output into the screen. Whereas our program, right, average echo in this case, right, should only output thing one. So thinking about it, our program, in our program, we do know how many arguments that we have, right, coming in. It's argc, right? It's argc. And we can access each value in that argv array through an index, right? So in this case, 1, 2, 3, 4, 5, 6. So, again, in C, when we're working with like arrays and things like that, we always have to kind of remember how many elements we have, right, in the array so that we can stop like iterating through in the for loop, for example. And argc is literally that value, right? It's the number of elements inside our argv array. So we can actually just iterate through this argv array right here, this argv array, argc times, right? So starting from 1 all the way up to argc, right? We can actually grab every single value by accessing the current index and just print it out, right? So it's just a for loop. For example, we can just do the same thing. For int arg index, right? We're going to start at 1 because the first index in the element pointed by that first index in argv is the program name. Just a reminder, we start at 1 so that we can grab everything else after that, right? Okay, so we want to keep going until we're less than, right? We'll keep going as long as we're less than argc, which is the total number of like elements in our argv array, right? So, however, it's not the index, right? So we can't just say less, because if we had 2 arguments, right, argc would be 2, and we're starting at 1. And I think that works, right? We're starting at 1. We'll only get the first one, even though argc is 2, because the first element is going to be the program name. So that does work, actually. So just thinking on the fly. So we'll have our basic for loop here, and then we can just get the value by tapping into argv with our arg index, right? And then we can print out the value with no new line, right? because we want to like print everything out in a way that makes it like in one line. And if we had a new line at the end, then we'll just have like a list of all the values. But we're kind of not done yet because if we were to do it this way, all our values would be like smashed together without any spaces. And I'll show you right now. So let's say this, like, let's say we have this. We're just printing out, we're blindly printing out everything in our argv array, right? We compile this -oa echo. Let me just make this here. Um, you see how everything's like slammed together and we don't even get a new line, right? So we have like two things we need to implement here. So in this loop, after we're done with this loop, we obviously need to print out a new line, right? So that's good. And let's actually check that out after we've done this. Okay, cool. Now we have a new line, but we need spaces, right? So the easiest way to do that, after each iteration, when you've printed out the string value, right, you just have a space behind it. Okay? Cool. But then it is kind of not exactly like what we specified here, because we do have a space at the end of world, right? So we could use an if condition to not print out a space if the arg index is going to be the last element, right? And in this case, the arg index would be the last element if it is one less than argc, right? So if arg underscore index, right? If, let's write that as a comment. If arg underscore index is one less than argc, right? What do we want to do? We don't want to print a trailing space, right? Otherwise, print a trailing space, right? So we can adjust our loop body to do this, right? So we'll still blindly just print out all values, right? But we'll have a check down here saying if arg index is basically equal to argc, right, minus 1, right? That means if arg index is less than is one less than argc, meaning that it's the last element. So if argc is 2 minus 1 is 1. If our arg index is 1, right, in the situation where we only have 2 elements in our argv, right, that does mean that if our arg index is 1, we're at that last element for that particular command, right? So then we'll print nothing, right? And then else, I think we can do it like this. We'll print a space, okay? So how can we make this better? Well, how about, right? How about we just kind of twist it around and say, well, if it's not, right, if arg index is not 1 less than argc, we'll just print a space. Otherwise, we don't do anything, right? So we can adjust to say something like this, and we can get rid of this. So that simplifies things a bit, right? And now we can test. Get rid of this. Cool. There we go. So it works the same way, right? So now we have pretty much cloned most of Echo, right? So the basic things about Echo. But the point is that, argc contains the total number of arguments that a command line has running your program. and argv will contain all the strings with it. So yeah, that's a basic way to, I guess, here we were able to use a for loop. We were able to access, an array. We were able to have some conditions, right? Condition checks. So I think we're making pretty good progress in learning more C. Okay, so that's our basic simple example. So let's move on to memory and pointers. So I've heard that pointers in C is one of like the hardest things to understand. So I've been trying my best to also like study it on the side just to make sure. So it's going to be a topic where we're actually going to move pretty slow on. But I think by the time we come out of it, at least we won't be totally lost. So. Um, yeah, let's just might as well just get started in reading the chapter together. Um, get on with it. Uh, okay, memory and pointers. What are you pointing at? Okay. Uh, is this how we read it? And of course, mommy never lets me stay out after 6 p.m. Thank heavens my boyfriend variable isn't in read-only memory. I don't get it. But maybe we will after reading this chapter? Okay. If you really want to kick butt with C, you need to understand how C handles memory. The C language gives you a lot more control over how your program uses the computer's memory. In this chapter, you'll strip back the covers and see exactly what happens when you read and write variables. You'll learn how arrays work, how to avoid some nasty memory snafus, and most of all, you'll see how mastering pointers and memory addressing is key to becoming a kick-ass C programmer. Okay, I'm excited. All right. Okay, so here's some tips. I guess I already see this. To best understand pointers, go slowly. Yeah, I'm guessing this is a very scary thing in general. Um, yeah, so I've so far, like, to give you a sneak peek, I haven't had too much trouble with this chapter, but it is like a little bit more mind bending for those who I guess are coming at this new. um, so C code includes pointers. Pointers are one of the most fundamental things to understand in the C programming language. So what's a pointer? A pointer is just the address of a piece of data in memory. Okay, so we know that a pointer, let's take some notes, right? Ugh, right here. Okay, so let's just, okay, pointers. So what do we know? A pointer is just an address to a piece of data in memory, right? So just to kind of refresh ourselves, an address, right? An address in memory is just a number, right? And depending on like what kind of computer you have, if you have like a 32-bit, computer, like meaning that your CPU addresses things like, sees things in groups of 32 bits, or if you have a computer that is 64 bits, meaning that your computer sees things in groups of 64 bits, like 64 ones and zeros, 32 ones and zeros, and so on. Basically, your address is going to be a number that big, meaning that if you have a 32-bit computer, right? So let me just write that as an example. Example, 32-bit computer sees ones and zeros as sees 32 ones and zeros as a unit, right? And 64-bit computer sees 64 ones and zeros as a unit. So what does that mean? It means that an address in a 32-bit computer is a 32-bit number. So address in a 32-bit computer is a number between 0 to 2 to the 32. So meaning you have around maybe 4 billion uh, memory addresses. So you count from 0 to like 4 billion or something like that. I think 4.2, something like this. I'll just say 4 billion, right? And then an address in a 64-bit computer is a number between 0 and 2 to the 64, right? And that's really big, right? Really, really big. But all that matters is that an address is just a number, right? So an address, a memory address, is just a number in that range, right? So like if you think about RAM, let me just, maybe I can, yeah, let's do this. Let's just start drawing. Scala draw. Okay, let's see if I can draw something. I have a little tablet here, right? And it's connected by Bluetooth, so I'm not sure if my computer is gonna pick up the thing. I think it is. So if I were to move my mouse, where is it? Oh, it's not working, is it? Let's see. Let's pair. Come on. Intuos. Intuos. BTS. Ah, okay. Okay. So, like, let's think of memory as like a big, like, storage, like partition storage, right? Let's just background. Okay. So, like, this will be memory. Okay. Just think of it as like a bunch of shelves, right? And we have basically, partitions in that shelf. Let me just use this. Ah, too thick. How do I undo? This is like the first time, so bear with me. Okay. Okay. So we have like little shells, right? These are places where you can actually put data, for example, right? So, you have like, maybe 52 here, you'll have maybe 120 here, you'll probably have like maybe 336. These are like values, right? So these are values, right? Values, right? Or data. Okay. So all these are values or just data. And memory addresses are actually just the labels, right, to that cubbyhole or shelf, right? Ugh. We'll get better at this. Don't do it often. So, memory address at 1, right? So, we say memory address at 1. What is that? That leads us to 52, the value, right? Memory address at like, let's say 4 gives us back 136, right? So this here, right? All of this could be a 32-bit number or a 64-bit, right? So this is only the first 7 addresses, but you potentially have up to like, I don't know, 2 to the 64 for most modern computers of these, right? And that's why like, we're going to see later on when we print out memory addresses, you'll get like really big numbers, right? Where they kind of look like, 0x, 1, 2, 3, 4, 5, 6, 7, 8, right? So that's like that signifies a memory address, right? And like we'll kind of get to learning about how to actually break this down later, but I kind of want you to just understand this analogy here. Like this is my analogy. It's like a, a big like shelf with little cubby partitions, and you just kind of label them, right? And these labels are basically memory addresses. Okay. All right. So, yeah, pointers are used in C for a couple of reasons. Instead of passing around a whole copy of the data, you can just pass a pointer. That doesn't make sense to me right now. I've got the answer you need. It's right here in the Encyclopedia Britannica, the copy of information you need. Or you can just look at page 241. This is a pointer, the location of the information. Ah, okay. So this one, I get it now. So like, let's say you have a function, right? And it takes in an argument, like a value, right? And when you actually call a function with that value, what ends up happening is that the C, like I guess the computer will like take that whole piece of data and actually just like brings it over to that function, right? Most likely it'll just copy that whole thing over and just bring it over, right? But with pointers, we just pass around the label, the piece of paper that has a memory address, right? So going back to this analogy, right? Let's just say, let's redraw this. Like going back to this analogy, uh, I think it's better off that I just do. I'm left-handed, by the way, so that's why it looks weird, like always slanted. Okay, so let's say I have memory address 0, 1, 2, and 3, right? And then I'll say, address at 2 is like 1,337. Okay, so instead of like passing around like this thing here, right, to a function where it looks like it's like where we have the label and passing this big thing around, we just pass 2 around, right? And I guess that is lighter because potentially you're gonna have like instead of right now we're just dealing with numbers, but we could potentially be dealing with strings, for example, right? Where we have lots of characters and we're gonna have to copy an entire group of characters, right? So like for example, we look at let's just look at mining, okay? 1, 2, 3, 4, 5, right? And let's just start with the arbitrary address at 21, 22, 23, 24, 25. And let's look at the ASCII chart just to make it real. Okay, I think this is good. Okay, so my name, let's just start with capital, right? So R is what? Is 80 in decimals 82, okay? And then O is in decimal 79, okay? Ooh, what? Did I just copied something? Weird. Uh, okay, 79, right? G is gonna be 71, right? And then E is gonna be 69. And then R again is gonna be 82, right? So this actually corresponds to my name if you look at the ASCII chart, okay? So like how it would work right now is if we moved memory around to functions, like let's say we want to pass the string, right, Roger, to a function, right? We would have to pass around this entire chunk of memory. Whereas like I believe in pointers, what they're trying to say is that you can just pass 21 and probably some information about where my name would end. And this is like false. This should have also contained 0 for the null character. Null character, right? We'll pass like maybe the address at 21 and maybe the length, which is 1, 2, 3, 4, 5, 6, right? And then we would have like some sort of inferring that since this is going to be a block of characters starting at 21 with length 6, you can just do whatever you need to do to access that data directly versus passing this entire block, making an entire copy and passing that around. I think that's what they're trying to say. So that's one. Next, you might want two pieces of code to work on the same piece of data rather than a separate copy. Okay, sure. You were supposed to sign the birthday card we left in the lunchroom, but I prefer this one. It's got kittens. Okay? Pointers help you do both things, avoid copies and share the data. Okay, that makes sense because if we're able to share the data, right, we're able to actually, since we know memory addresses of things, we can actually poke around and modify these things, right, these values. So I think there's like a motivation, right? But if pointers are just addresses, why do some people find them confusing? Because they are a form of indirection. If you're not careful, you can quickly get lost chasing pointers through memory. The trick to learning how to use C pointers is to go slowly. So then here's a tip. Relax. Don't try to rush this chapter. Pointers are a simple idea, but you need to take your time and understand everything. Take frequent breaks, drink plenty of water, and if you really get stuck, take a nice long bath. Okay, good tips. I like the water tip. Okay, next page. Digging into memory. So to understand what pointers are, you'll need to dig into the memory of the computer. Huh. Every time you declare a variable, the computer creates space for it somewhere in memory. If you declare a variable inside a function like main, the computer will store it in a section of memory called the stack. If a variable is declared outside of any function, if a variable is declared outside of any function, okay, it will be stored in the globals section of memory. Oh, okay. All right. Okay. So maybe I can kind of help. Now let's keep going. So we'll have this piece of code here, right? We'll say int y equals 1, and that looks like it's outside the main function, right? So basically, this variable y, this will belong in a cubbyhole in a globals section, right? This y is actually an alias to a specific address. Just think of it that way. And that's what it is. Like variable names are just labels for an address, right? So at address something at y, the value stored in there is 1. So inside a function, right? So if a computer, if you declare a variable inside a function, the computer will store it in a section of memory called the stack. So this x here with 4 is going to be in this stack section. Okay. The computer might allocate, say, memory location 4,100,000 in the stack for the x variable. So the x is actually labeled 4,100,000. So address 4,100,000 is the same thing as saying x, right? And the value in x is 4, or we can say the value in location 4,100,000 is 4. Okay? If you want to find out the memory address of the variable, you can use the ampersand operator. So then printf x is stored at %p, right? And the address of x to replace this %p, right? So %p is a formatter for addresses. It's actually going to format in a way that I mentioned before that looks like this, right? This 0x whatever, that's hexadecimal. It'll format addresses that look like that. So x is stored at 0x3e8fa0, right? The address of the variable tells you where to find the variable in memory. That's why an address is also called a pointer. So address, pointer, they're both the same because it points to a variable in memory. Okay, so that's interesting to think about. So a variable declared inside a function is usually stored in a stack. A variable declared outside a function is stored in globals. Okay. I don't know. I think this is kind of hard to like understand maybe. But let's try to kind of digest that information. So remember I said there was like memory is kind of like a cubby hole, right? Or a shelf with cubby holes. Well, actually, inside this shelf, right, there's going to be a partition, a certain partition of it, right? That is for our program, right? So let's just say here, this is where our program lives. Okay, we get a bunch of these cubby holes for our program, right? So just think of it this way in physical memory. This is our program, right? Our app. Let's just say app, right? And if we zoom in into just this section here, right? We have basically a cubby sub shelf, right? With our own cubby holes, right? Okay. So like going back up here, this is our app, and this could be, I don't know, like just think of it this way. This could be like what's a good app? I don't know, VS Code, right? It's oversimplified. It's really oversimplified. Okay, so just stick with me. So if we zoomed in here, like our own app right here, it's gonna look like this, right? A subsection, right? And we'll have addresses like 1,000. We'll have like 1,001. We'll have 1,002. We have 1,003, 1,004, and 1,005, right? Basically, our app gets a piece of memory that starts at some address and ends at another address, and and so on. Now, this is not entirely correct because actually, furthermore, we are divided. Like our app is divided into separate sections of memory, right? So in this case, it looks something like this, right? And these sections of memory, for example, like the green part is, could be code, right? And then the orange part, could be, in this case, globals, right? And then, red part could be whatever, could be heap. We missed, let's give a blue right here to be constants. And then up, all the way up, stack. So thinking back at it, we have way more than 6 memory addresses. We have a lot of memory addresses. Okay, this can start, I don't know, potentially at 1,000 now, and then we can end at like maybe 3,000, for example. Okay, so actually, that's like more closer to what memory looks like. In our app, right? So we go from basically like overall here, zooming into our like overall physical memory here, zooming into just a section that we care about in our app, and if we furthermore divide our app into specific section of memory, and actually in this section of memory, right, we also have our own cubby holes, right? Even like that's where the cubby holes exist, right? Right. So if we look at, let's say, zoom into the heap, for example, right? The heap can then just be its own small, shelf with specific addresses. Let's just say, maybe it starts at 1,300 and then ends at like maybe 1,400, right? And that's where all these addresses are living in. So this could be like 30, right? At like maybe 1,350, right? So then you have something inside the heap here. Okay. Usually things like code is just basically your program itself because everything runs in memory, right? Like you don't run your program off from disk. Whenever you run a program, your operating system takes that program and puts it into memory, right? So the code of your program is actually living at the bottom, right? And then we have all our constants defined and the globals. Again, globals are things outside of our function. And then we have heap, which we'll talk about later, and then stack is any temporary data for that function, right? And just spoiler alert, like every time you return from a function, you clear those variables in stack, so you empty out those memory locations. But um, all that, like, not super required to know now. Just know that, like, this is how memory kind of looks like for your application, right? It's divided. Although we start out with, like, uh, a shelf with cubby holes here, you actually only have a subsection for your app, and then your app in turn has its own individual sections for specific purposes. Okay, so uh, sure. Okay. Set sail with pointers. Imagine you're writing a game in which players have to navigate their way around the Bermuda Triangle, the Bermuda Rectangle. Okay, different. This game will need to keep control of lots of things like scores and lives and the current location of the players. You won't want to write the game as one large piece of code. Instead, you'll create lots of smaller functions that will each do something useful in the game. Okay, so you want to do things like go southeast, go northwest, speak in present tense, go south. Okay, so all these functions here that you can do in your game, all right? So what does any of this have to do with pointers? Okay, let's begin coding without worrying about pointers at all. You'll just use variables as you always have. A major part of the game is going to be navigating your ship around the Bermuda Rectangle. So let's dive deeper into what the code will need to do in one of the navigation functions. Okay, set sail southeast, Captain. The game will track the location of players using latitudes and longitudes. The latitude is how far north or south the player is, and longitude is her position east or west. Okay, so latitude is like vertical, right? I have this now, I can practice. So latitude, lat is vertical, and longe is horizontal, right? Wait, no, is that how it works? Yeah, the longitude is her position east or west. If a person wants to travel southeast, right? So basically, what's southeast? It's this way, right? So SE. Okay. Uh, that means her latitude will go down. That's true. Her latitude is going down. So let's just do that. I have no clue what we're doing. So lat is going down. And then her longitude will go up. That is true. So then longe is here. Okay. So as we are, okay, that makes sense. So then we have this piece of code here to go southeast, where given some latitude and given some longitude, we're going to decrease the latitude. So we see that we are decreasing the latitude here, right? And then we are increasing the longitude, so we're adding by 1 right here, right? And then we have our main function that will test, basically calling this function and getting some value back. Okay, so what we're expecting here, and we have to read this function very carefully, is that when we receive these two numbers, this latitude and longitude, we're going to subtract from the latitude by 1, so decrement, because we are decreasing in latitude, and we are going to increase the longitude, right, by 1, which is, an increasing fashion, and then we just return from the function, but we don't return a value, right? We just modify the variables given to us here. I know where this is going, okay? So here's the function that will test that. So we'll first initialize latitude to be 32, okay? And then we'll initialize longitude to be negative 64. And we'll call go southeast with 32 as our latitude and negative 64 as our longitude. And then we'll do the subtraction where we expect something like in this case given latitude is 32, we want to turn that to 31, and then negative 64, we want to transform that to negative 63, right? So then when we're printing, we should say avast, right? Avast now, at, I guess, 31, negative 63. Something like this. That's our expected, right? But it's already hinted here that's if the code works. So the program starts the ship at location 32, negative 64. So if it heads southeast, the ship's new position will be at 31, negative 63. Okay, so will this code work? Why? Why not? I say this code doesn't work because we didn't return any value, right? And also, I don't think, whatever arguments we pass into functions with the way it is right now, we can't just modify them and have them work outside that function, right? Let's actually write that. So create a new project. This is lat long, right? Let's do lat long. New file, main.c. Okay, so again, include stdio.h int main, and I'm going to start defining my main function as int argc, character pointer, argv as an array. Even though we might not do anything with it, return 0. Okay, so we're going to have a function called void go south east with 2 arguments, right? And then we're just going to decrement latitude, and we are going to increment longitude. Okay, and then in our main function, we'll define a latitude to be 32, starting one. We'll define longitude to start at longitude, all right, to be negative 64. Then we're gonna call go southeast with our latitude, which is 32, then longitude, which is negative 64. Then we'll just print avast now at. Okay, we're gonna print formatted. I think we decided that %i and %d are the same, right? So I'm gonna just be consistent and do this %d instead, right? And then new line. Then we'll say latitude, longitude as the replacements for the placeholder, and we can actually compile and run our program. So we go back to our terminal. We're still in average echo. Where are we at? Lat long. CD lat long. Okay. We'll do gcc main.c. O lat long. Then we'll invoke lat long. Avast. Now at 32, negative 64. What did we expect again? We said avast now at 31, negative 63. Same thing here. But the program didn't work. It gave us 32, negative 64. We're going to have an explanation coming soon. Boom. So the code should move the ship southeast from 32, negative 64 to the new location 31, negative 63. But if you compile and run the program, this happens. That's exactly what we got. Avast now at 32, negative 64. WTF, the ship is still in the same place. The ship's location stays exactly the same as before. Okay, now here is the important fact. C sends arguments as values. Okay, what does that mean? The code broke because of the way that C calls functions. Initially, the main function has a local variable called longitude that had the value 32. Okay, when the computer calls the go southeast function, it copies the values of the longitude variable to the long argument. Okay, so different variable, right? When you call a function, you don't send the variable as an argument. You just send the value. So it's not about the variable naming here, actually. When you call a function, it's not that you have a different variable name that changes it. It's not because of these two being different from these two. Okay, so just to clarify, when you call a function in C, the computer will create copies of these values in memory, like another 32 and another negative 64. And then this function will receive those values and do stuff with it, right? So when go southeast function changes the value of lon, right? The function is just changing its local copy. So the copy that was received by calling the function is the one that is being modified, not the original. Okay. This means that when the computer returns back to the main function, right? Meaning that you're done with this go southeast, right? The longitude variable still has its original value of 32. Okay. But okay, so let's draw again. So at some point, let's say in main, right, we have two variables, right? Latitude is going to be 32, and then we'll have longitude. It's going to be negative 64, right? So this is main, right? When we call main, okay? And then we're going to call go southeast, which is a go SE, okay? And we take in a lat, and we take in a lon, right? So, so we can zoom out a little bit. This is way big anyway. Let's see here. Oh, here. Get some more space, right? So if we take a look at, and how do I move? Cool. Okay. If we take a look at how memory works, just again, right? At some point inside this main function, there's like a stack memory, right? Inside the stack memory, lat points to maybe at address, so lat is now 32 here, and then lon, right, just for convenience, is going to be negative 64, right? When we call go southeast latitude with 32 and negative 64, what ends up happening here is that there's two more variables that get created here for that function, okay? For that function, right? Two more variables get created because this, as it turns out, let me just write it. So lat is going to be 32, longe is going to be negative 64. Okay. It's going to return a separate copy, right? As it turns out, if we go back to the memory model here, right, where we have stack heap globals constants code, as it turns out, one thing to know is that whenever you call a function, every function gets a new stack for it to use, right? It's a very temporary stack. Okay. So that's the reason why they're actually just copies, right? Because a new stack is allocated just for this function call, and the arguments here are actually assigned as values inside this new stack, right? So that's the reason why values are copied, right? As it is. So that explains a lot why, whenever we change something inside Go, southeast, right, and we didn't return any value back to the caller, we had expected our variables to be modified, but they weren't because actually the go southeast function was actually modifying its own local variables here. And these two latitude, longitude variables are actually local to main. So actually they have no connection with each other, right? So that's the reason why. Every time you call a function, you get like a separate stack. And then when the function is gone, you blow away that stack, right? So when you're done with go southeast, the stack just becomes free memory again, automatically. But you can actually solve this problem where you can actually share variables around function calls if you use pointers. So like instead of like, um, you know, passing around true values, right? 32, negative 64, right? Why don't you pass a location to the value, right? Instead of passing these guys directly the values, why don't you pass this here, which is basically a number, right? You pass it in as a number, and then since you know that it's an address, why don't you just go to that address and modify that number instead? Instead of passing the value itself, why don't you pass the address, and your function knows that you're getting an address. Modify your function to take in an address, operate on the address by going to the value there, and then actually doing something with it. So in this case, if this address is maybe 1,030, and then this one's 1,031. I keep doing 1,030 because I have a video card that's a 1030, I guess. But anyway, erase that. I don't want to confuse anybody. So these two, right? Instead of passing in 32 and negative 64 to go southeast, why don't you pass in 1030 and 1031, right? And now these don't become integers anymore. These are not values. Instead, the go southeast function has to read them as memory addresses and actually go and dig into them, right? Go and dig into these, get those values and modify them in place. Like turn this into 31, turn this to 63, and call it done, right? So that's like the general idea. Like we call this like just give it some indirection, right? Instead of going, it's because technically when you are calling the function, you are making copies of the address, but you know these are addresses already. You're not really, nothing really changes, right? You're still allocating a new stack, right? So these two are still stacks, right? But, instead of copying the real values of 32 and negative 64, why don't you just copy those memory addresses? And in your function, the logic will just know that they're memory addresses and just go into those addresses at those locations and modify whatever's there. So I think that's what they're going to do right here. So yeah, try passing a pointer. So address, pointer, same thing, right? We pass a pointer, pass an address. Okay, so we make, instead of like having to make a copy of that value, we just instead make a copy of the memory address or the pointer, right? So instead of passing the value of the latitude and longitude variables, what happens if you pass their addresses? If the longitude variable lives in the stack memory at location 4,100,000, what happens if you pass the location number 4,100,000 as a parameter in the go southeast function? Okay, so we can think of it as like passing the slip, right? The paper that says, oh, go to 4,100,000. That's what this picture is showing, right? This 4,100,000, I guess, locker has the value 32. Instead of ripping off that locker, creating a copy of that locker, and then putting it in another place, you can just pass that paper around, clone that paper, and pass it. Hey, here, you can have this slip of paper. I don't care if I don't care if you lose it or not, right? The slip of paper just tells you the memory address to look at, and you can come to that locker and do whatever you need to do, right? So if the go southeast function is told that the latitude value lives at location 4,100,000, then it will not only be able to find the current latitude value, but it will also be able to change the contents of the original latitude variable. Okay? Because you're going to the real address and modifying it now. All the function needs to do is read and update the contents of memory location 4,100,000. Okay? Because the go southeast function is updating the original latitude variable, the computer will be able to print out the updated location when it returns to the main function. Because, again, variables are just kind of labels to the memory address. So if you, in a function, right, one function, a separate function, if you have modified the value at a certain memory location, outside the function, when something else is referencing that memory location, it's going to see that same value because you've touched it in place, right? So that's the whole point of pointers, right? Pointers make it easier to share memory. This is one of the main reasons for using pointers, to let functions share memory, right? The data created by one function can be modified by another function, so as long as it knows where to find the memory. The data created by one function, in this case main, right, can be modified by another function, go southeast. So as long as the go southeast, that function, knows where to find it in memory. So the only way it knows how to find it in memory is if you give it the pointer, give it the address, right, to go to the real location, that address, and mess around with those values inside. So now that you know the theory of using pointers to fix the go southeast function, it's time to look at the details of how you do it. Okay? Okay, so let's do this Q&A right here. So I printed the location of the variable on my machine, and it wasn't 4,100,000. Did I do something wrong? You did nothing wrong. The memory location of your program the memory location your program uses for the variables will be different from machine to machine. Yeah, that's true. It just changes all the time. Why are local variables stored in the stack and global stored somewhere else? Local and global variables are used differently. You will only ever get one copy of a global variable, but if you write a function that calls itself, you might get very many instances of the same local variable. Because when you call a function, you get your own stack, right? What are the other areas of the memory used for? You'll see what the other areas are for later on. So, okay. Again, let's really go slow on this chapter. Let's just digest every page, right? I know it's long and painful, but it'll be worth it, I think. At least I'm understanding it better now after giving a second read through. Using memory pointers. There are 3 things you need to know in order to use pointers to read and write data. Okay, so this is how we use pointers, right? To get the address of a variable, right? To get the address of the variable, we need to use the ampersand operator. Okay, so we denote, like, to get the address, we have to write ampersand, name of the variable, and that actually returns us back a number, right? That number is the address. Okay, don't be thrown off by the %p. That's just the way to print out the address in a form that looks more like, techie, the 0x ABCD kind of thing. It's bottom line is it's just either a 32-bit number or a 64-bit number. Chances are it's a 64-bit number if you're on like a computer that's not over 20 years old. I look at mine because this computer is like 4 years old, 10th gen Intel, something like that, 4 or 5 years old. Um, yeah. So, um, so that's how you access um, a memory address of a variable. You use an ampersand, right? So, ampersand. So, let's see, right? In this case, latitude would get us the memory address of the latitude variable, right? And that will then return us back for, in this case, right? That will return us back 4,100,000, right? Whereas latitude will return us back 32, right? Putting these two together, right? It's literally just this. If you look at this, that is 4,100,000, something like that. Cool. Shouldn't have done that. It's just, yeah, good enough. All right. So yeah, once you've got the address of a variable, you may want to store it somewhere. To do that, you'll need a pointer variable. Okay. So actually, I did say something like this. Let's just say lat. So this pen has like a little button here, right? And since I'm left-handed, it's really hard to like avoid it. So I have to like hold my pen like this, and sometimes I might click on the button accidentally. It's just the world that we live in. So, okay. So we'll have, let's say we have this, right? I mentioned that we can reference a memory address of a variable with ampersand. This is not exactly an integer, right? It's a different type, right? Called a pointer, right? Pointer to an integer. It's a different data type. We call it the pointer to an integer. Okay? So how that is that it is actually this type. Int star. Okay? That is the real data type of whatever is returned by this. Okay? So if we want to assign this to some variable, for example, we would have to have something like this. Okay? Why? Why do we need to do something like this? We know it's a number already, but why does it have to be so special? Why does it have to be a pointer to an integer rather than just an integer, right? Well, the thing is that, again, like I said before, sometimes we need to modify our function to take in memory addresses, right? And then knowing that, our function knows that we're getting memory addresses, and then we can dig into the real value elsewhere in that real address. Well, if you left everything, if you just think about it, right? If you left this here, what is returned by this, as a regular integer, how would you know whether or not it's a memory address or a real value if you were to pass it to a function? Right? So you have to be able to distinguish whether or not something is a value or just a memory address, right? Which will potentially either lead to another value or maybe another memory address in general, right? We'll talk about double pointers maybe down the line. But what I'm saying is that, the int star, and now just int star, you'll have like, character star, you'll have double star, you have float star. Like these are just pointers to an integer, pointers to a float, pointers to a double. It helps us tell whether or not, what we're seeing here is either a real number or like just a number that represents an address. If we know something is an int star, then we don't. We go, whoa, wait, no, this isn't a value. This is a memory address, which would probably give us a value if we were to do something with it, right? And that's the reason why. And you'll see that in code later on. But once you've got the address of a variable, you may want to store it somewhere. To do that, you will need a pointer variable. A pointer variable is just a variable that stores a memory address. When you declare a pointer variable, you need to say what kind of data is stored at the address it will point to. See? Like this. Bottom line is still a number, right? It's still a number, but it helps the compiler, it helps you as a programmer tell whether or not, what you're actually operating on, this little integer, is actually either an address or a value. So you can read the contents of an address, right? When you have a memory address, you will want to read the data that's stored there. Let me read that again. When you have a memory address, you will want to read the data that's stored there. You do that with the star operator. So you star that address to get the value inside. This is how you dig in, right? Given this memory address, we know that this address, right, is a pointer because why? We declared it as int star, right? And now let's say, we pass this around and we want to now get the real value of it, right? What do? Well, we can get the value of it by preceding it with a star. I know, super confusing, because in one case, you're using the star to declare as a memory address. In another instance, right, you're using the star to dig into it, right, to dig into the memory address and get the value. It's super confusing, but let's kind of keep going with this number 2 here, and then let's dive deeper. The star and the ampersand operators are opposites. The ampersand operator takes a piece of data and tells you where it's stored. So that's easy. That's to get the memory address, right? The ampersand tells us to get the memory address. The star operator takes an address and tells you what's stored there. Okay, so star, variable name, give me the value stored at this memory location. This star x, star y, star z only works if x, y, and z are pointer types. Okay, so you can't just willy-nilly declare something like this. Int. You can't just say int b, right, equals 3, and you can't just say star b. You can't just do that. That's not going to work because this is not a memory address, right? This is just a regular value, right? So this b has to be a pointer, a memory address already. So it would work if this is here, right? But that would mean that 3 is not a value anymore. It's a memory address. So this star b, if means that, instead of having it here be a value, it's not there. It could be, some location here that points to maybe, let me try something different. 1,500. It could be 1,500 instead. Because, when you have this, you've turned something into a memory address. This is now being read as a memory address. And when you dereference with star, right, b, it means that you want to go into this memory address at 3, find that value, which will then give you back 1,500. Okay, so you have to be careful. Int star and int are two different things. Okay, now let's go back. So that's so this that was not good. This, right, is to say get the, why am I even doing this? I can just type it. So this here can mean get the address of the variable, right? Then when you do that, when you do this, the address becomes some pointer type. Okay, you know, you've received back an address, but it's a number. This number is going to be a pointer type. Okay, now this one is a little bit tricky. It depends on which side it is showing or it is being used, right? So if it's on the what we call if it's on the L side, right, the left side, such as int star x equals 3, right? We are saying that 3 is a memory address assigned to x, which is a pointer to an integer. Okay, so x is now a pointer, right? And what's inside x, we don't know. Like what's inside that memory address, we don't know. But we know that the memory address is 3, right? The R side, the right side, such as int y equals star x, right, means we are taking the value stored at, you know, the pointer x, right? Because x is a pointer type, right? You know, taking that value stored at the pointer x, so the address of x, right? Meaning at location 3 and assigning it to y. For example, location 3 could be containing the value 1500, so y has 1500. Make sense? So star is a little bit more confusing, right? Star, depending on which side it is on, if it's on the left side, right, it's going to be declaring a pointer type, right? If it's on the right side, it means you want to get the value of that current pointer variable, right? You can't use star on any, yeah, you can't just like say, oh, star, for example, let's say this is, when star is on the R side, you can't just take the value of any variable. The variable has to be a pointer type, right? Therefore, something like star y, right? Then we have to assign it to something in z, star y, right? Won't work because y is an int type, not a pointer to an int at all. Okay? So we have to understand it in this way, right? I know it's hard to like really, you know, make sense, but it's like we got to practice, and I'm, you know, I think practicing together is the best way to do this, and that's why I say it's gonna be long and painful, but it'll be worth it. It'll be worth it. Okay, so now we can actually change the contents of an address, right? If you have a pointer variable and you want to change the data at the address where the variable is pointing, you can use the star operator again, but this time you need to use it on the left side of the assignment. So that's how we can actually change the contents, right? Yeah, we do star blah equals 99. It means to dig into the memory location, right? The value at the memory location. Starting to get tired. And change the value there, right, to whatever you want, right? So that actually alters our L side definition. Now we need to add more to it, right? So the L side, right, such at for declarations such as int pointer x, right? So declarations, L side star declarations, declarations. Only we do int star, char star, float star, double star. It means to declare this variable to hold a memory address, right? But if star is on the L side, left side, right? Without declaration, such as z equals 78, it means to change the value of located at the address of z to 78. So we'll update, right? So not change the value, update the value, modify the value. Okay. So for L side, in one instance, when we declare things, the star is used to say, hey, this is going to be a pointer type. But if we're not declaring and we're using star in an assignment, right? In an assignment on the L side, we're changing the value. Now, if star is on the right side, right, it means that we're getting that value. Okay. And the caveat on the right side is that you can't just star anything. You have to star already a type that you have to star or dereference any variable that has already been declared to be a pointer type. So you cannot just dereference any type of variable, only pointer types. Okay. So here's where we actually modify the code to fix this, right? Okay, I think this will be the last example, and I have to take a break for today. I think we've been going quite long too. But let's modify this code, right? So again, like I said, this go southeast, we shouldn't really be interested in, making copies of it. Instead, we should think about receiving memory addresses, right? So why don't we say we want to receive pointers to an int, right? So pointers to an integer named latitude, pointers to an integer named longitude, right? And now these will be actually memory addresses, right? So we want to assign, right? We want to assign, right? Going back to our notes, we want to assign new values to the memory address. So that is actually putting a star on our left side, right? Because we want to assign a new value to latitude, but we want to make sure that we modify those values. So latitude has a star here. But at the same time, we also want to get the value at latitude, so we had to do it right here too. So get the value of latitude right now, right? Which is going to be at 32. Subtract 1 from it, which is 31, and assign it to the location of latitude right now. So there's lots of things going on with stars here, right? Again, on the right side, we want to get the value at latitude, so we do that first, right? We do our math second. Finally, we use star again on the left side to say, hey, let's actually update the value at that memory location. So right here, right? But if star is on the L side without declaration, such as this, which matches this format, because if you think about it, it's just the same thing as this, right? Or, sorry, this, right? Such as this, it means to modify the value located at the address of Z278, meaning we're going to modify the value, right, currently stored in the address of latitude with this operator here to 31. So we'll do the same thing here, right? Okay. And then now we have a function that will actually modify values in memory, right? But this also changes too. Like if we simply can't just do it this way. Watch, if we were to try and compile right now, we would actually get an error, right? GCC main.c. We get an error, and the error is going to say, well, you're passing an argument that is assuming to take in a pointer, but you're giving me an integer. I want a pointer to an integer, but you're just giving me a straight up integer value. Are you sure you want to do this? Right? And these are warnings. It's not going to stop you. It's not going to stop you because guess what? Integer values, right? And pointers are both the same. They're just integers. They're just all numbers. So it technically works. But when you're doing that, what ends up happening is that, in this case, latitude is 32 here when we're calling it. Then when we receive it, we're going to think that, oh, we want to dig into the value address 32, not value 32. So it's really important that we actually, instead of passing in the value, now we'll pass in the address, right? The address to that value. So how do we do that? Well, remember, to get the address or the pointer to that value, we use the ampersand, right? We use ampersand. Get the address of the variable. So we just need to say this. Get the address of latitude, which turns into a pointer. It turns into a pointer, right? It becomes some pointer type. So this is actually an int, but when we do ampersand, whatever, it becomes a pointer to an int, which is what we declared here. We're expecting a pointer to an int. So we'll do that same here. Okay? And that's, I think, all we need to do, right? Because these are still values, right? But here we're saying we want to pass the address to the value. Okay? So that's fine, I think. We'll compile. So no errors, right? Let's test. So we get what we want now, right? Because we're actually modifying directly the values in memory, right? And we didn't return anything from our function at all. We didn't return anything from our function, right? But we poked into the little cubby holes in our shells, and we kind of just messed around with those values. And when we actually look back at them again, after our function call, we saw that they're updated. And I believe the answers are here, right? So yeah, we did the same thing. Int star, star lat, star long, ampersand latitude, ampersand longitude. Okay, so I think I have a tip here. I just realized I would always, when I encounter something like this and you're trying to link the rules together, right? The rules of the L side right here. Try to evaluate from the right side to the left side, right? So, in terms of order operations or precedence, try to digest this part first and kind of convert it, and then see if you can apply the other rule to star once that's simplified. So in this case, what I did was, okay, well, I was like, star lat -1, right? That means to take the value stored at latitude, right? The memory address pointed by latitude, right? Take that value, subtract it to 1. So it's going to be 32 minus 1, right? To be 31. Right? Then we simplify all that and say, well, now we want to assign 31, in this case, on the L side, where it's not a decoration, but it's just a normal assignment, right? We want to update 31, or update the value pointed by latitude to 31. So that's how we're reading it. So we have to go really slow when we encounter statements like this. Okay? Okay, so yeah, let's just read the bullet points. So variables are allocated storage in memory. Local variables live in the stack. Global variables live in the global section. Pointers are just variables that store memory addresses. The ampersand operator finds the address of the variable. The star operator can read the contents of the memory address, and the star operator can also set the contents of the memory address. Right? So it's like the star operator is overloaded here. In one case, you can read the contents of the memory address, right? And that's usually going to be on the right side. And then the star operator on the left side is going to say, well, set the contents, right? um, and then there's a third one there in the declaration, right? In the declaration where it says, data type star blah, that is also a third type where we're creating a new memory address label, right? So it's just okay. I'm gonna stop here. I'm tired. But I hope this was useful. And again, this is intentionally really hard. I think pointers is what messes everybody up in C. It did for me when I did it in school a very long time ago, and that's the reason why I'm not a C programmer today or a C++ programmer, because I think it scared me so much that um, I never really bothered to dive deeper into it. But uh, I'm motivated now, and I'm going to make sure that I'm at least coming out better at it at the end. So, um, see you next time. Bye.